This is the first of a set of videos for Math 151 on the squeeze theorem. The point of these videos is to give you another introduction to this and show you what the squeeze theorem can do beyond what you've seen from it in class already. This first video will talk about what the squeeze theorem is, why it's important, and why it should be true from sort of a conceptual sense. The proof of it's well beyond what we're talking about in this course, but having an idea as to why it is true can be helpful when you're trying to use it to solve problems. The rest of the videos of this set will go over examples of how you can use the squeeze theorem to solve different problems. Why is the squeeze theorem important? Well, the main thing that it gets us is the ability to determine that limits exist and find out what they are equal to when we couldn't do it otherwise. And the main benefit here is the showing that they exist part of this. For all of our limit laws that we have in sections 2.3 and 2.4 for continuity, we need the limit to exist, and then we can say something about it. Here, this also gets us that limits exist in certain conditions. So let's see one example of what this might look like, and then go on to the actual statement. So a main example of a function that has this property is something like x times sine 1 over x. This here is the graph of x sine 1 over x. If you wanted to try to evaluate the limit at 0, you would think, oh, let me just try using the product rules we have from section 2.3. However, if I look at the limit as it goes to 0, and then try to split things using the product limit law, I have a problem here, as this limit here does not exist. Which means I can't use this law to try to simplify this limit. However, if I stare at this graph, it surely does look like the limit's going to 0, right? As I pick points closer and closer to 0, the y value is going in towards 0. That's what this graph is telling me here. So the limit should be 0, but based on our normal product rules for limits, we don't even know the limit exists. We have no way of saying that from this outset here. So this sort of thing is what the squeeze theorem allows us to do. It allows us to say this limit exists and its value is 0. We'll get there. That'll be the first example we do in the second video here. That's where we're headed with these videos. What does the squeeze theorem actually say? So what I need for the squeeze theorem is I need 3 functions. I need f of x, the function I care about, as well as 2 other functions, u of x and L of x, where u of x is an upper bound or bigger than f, and L of x is a lower bound or less than f, all on some interval around some point c. And now here's the conditions I need for u to be bigger than f and L to be less than f everywhere except for c. Now, this just gives me that f must be between L and u everywhere. To actually get the squeeze theorem, I also need L and u to pinch off at the same point. So I need that at this point c, both L and u limit to the same value. If I have all these assumptions, the squeeze theorem then tells me that the limit of f as I approach c must exist and must also be L. Right, keep in mind, I did not need to assume that the limit of f existed before I got to this last line. I got that for free as a conclusion of the theorem. Let's look at some pictures of this and see how this sort of looks in terms of what these functions must look like. So here's the main pictures you want to have in mind for the squeeze theorem. On the left here, we have just the inequality case. We have just that f is trapped sort of between u and L, where u is bigger than f and L is less than f everywhere. On the right here, we get the actual picture for the squeeze theorem. Not only is u bigger than f and L less than f, but we have the squeezing condition, where at this point c, both u of x and L of x limit in towards the same value L. The main thing you want to think about here is since f is trapped between u and L go to the same point at a certain value, there's nowhere else for f to go. F has to exist and go to that same point. This is what we get for the squeeze theorem. We'll see in future videos how we use this to solve problems, but as of now, here's the statement of the theorem. So why should this theorem be true? Well, we talked about it a little bit on the last page with the pictures, But the idea is if I have this squeeze set up where I have both the bounds of L and U and they both go to the same value, there's nowhere else for f to go. So I'll draw a picture here now to show you what could happen if you only have L less than f and U bigger than f, but not this squeeze condition. You can still have problems. So here's a possible picture that can happen. I have here that the inequality condition there is satisfied. That is that L of x is less than f of x is less than U of x everywhere on this interval. But I don't have the limit condition. That is, the limit as I approach C of U of x is not the same as the limit as I approach C of L of x. They're different values. And what can happen inside here is there's a jump. So in this case, the limit as x goes to C of f of x does not exist, because it has a jump in there. That limit does not exist. However, if I force L and U to pinch off to the same value, there's no room for a jump, because f has to stay between L and U are both going towards the same value, so it's going to have to be forced to do whatever it has to do, but it's going to have to go to that point on the inside. I'll draw another picture that shows something of this type now. And here's another picture here. Now pretend that graph's an actual function, but the idea is the same. The graph can be as crazy as you want it to be. But because L and U both pinch off at the point in here, this limit's going to have to exist and going to have to be the value where they cross. So in this case, I have both conditions, the inequalities and the squeezing part, and that gives me that this limit has to exist. Now you can see from this picture, there's nowhere else for f to go. It has to go to that point L at the middle there. So that's sort of a motivation to why this theorem should work. The actual proof is well beyond this course, so we're not going to talk about it. That gives you an idea of where we're headed going forward. So the next videos will go through some examples of problems you can solve using the squeeze theorem and how to use this theorem to figure those out.